and welcome to CPFD's Getting Started with Virtual Reactor 25.1 webinar. I'm Rosemary Clark, Senior Support Engineer for Barracuda Virtual Reactor, and I'll be your host for today's session. Our presenter will be CPFD's Sam Clark, and we are pleased to have this opportunity to provide you with an overview of the new features and enhancements integrated into the 25.1 release of Barracuda Virtual Reactor. Today's webinar is being recorded and will be posted on CPFD's Webinars and Presentations webpage under the Resources tab. If you want to review any information for future reference or share the webinar with a colleague, the recording will be available in the next day or two. So please submit your questions during the webinar by clicking the orange arrow to access the question panel. We've set aside plenty of time after the presentation to answer them, and your participation makes the session more engaging for everyone, and it's likely that others share your questions. And for those of you joining us who are new to CPFD software, allow me to offer a quick introduction to our company. At CPFD Software, our core mission is to advance multi-phase simulation technology for complex fluid particle systems, with a primary focus on fluidized bed reactors. Our flagship product, Barracuda Virtual Reactor, is the industry standard for modeling 3D transient hydrodynamics, heat balance, and chemical reactions within industrial units. For over 15 years, our clients have successfully utilized Virtual Reactor to significantly boost the reliability and performance of their systems through high-fidelity simulation. For engineers managing existing units, virtual reactor simulations offer a unique ability to look inside your system. This allows you to swiftly determine the root causes of underperformance and use virtual testing to thoroughly de-risk any proposed operational changes. For companies pioneering new technology, Barracuda is a powerful tool to accelerate and broaden your R&D efforts. It allows you to rapidly commercialize, scale up, and effectively communicate the unique technical capabilities of your technology to partners, customers, and stakeholders. The presenter for today's webinar is Sam Clark. Sam is the Barracuda Virtual Reactor Product Manager and has been at CPFD since 2008. He works closely with CPFD's development team to design features and capabilities for Virtual Reactor that benefit our customers all over the world. And I'll turn it over to you now, Sam.
Okay, I appreciate that introduction, Rosemary. And thank you all for taking the time to join us today. We are proud to announce the release of Barracuda version 25.1. Our development team has been hard at work implementing new features that we think you'll enjoy using. A reminder for our current users, you should have received our release email earlier today. If for any reason it hasn't reached you, please let us know so we can update your contact information. You can download version 25.1 right now. It's available on the CPFD support site dashboard. Everything we cover in this presentation is fully documented in the release guide chapter of the user manual, where you'll also find convenient links to the in-depth documentation sections. An area we focused on quite a bit for 25.1 development was Thermal Wall BCs. The most significant feature is the ability to specify heat transfer rate or heat transfer flux. Previously, wall temperature was the only available option, and users had to utilize a controller script to dynamically adjust wall temperatures to meet heat duty targets. But now you can more realistically and conveniently specify known heat transfer duties. This feature is available when using specify values or when using transient files. The Thermal Wall BC Manager allows for an unlimited number of thermal walls, each with its own specification, so you can mix and match temperature, heat transfer rate, or heat transfer flux among the various thermal wall BCs in the way that best suits your situation. Along with the new thermal wall BC input options, we've also made two enhancements related to output. First, data related to thermal walls is now output to wall zones in TechPlot. This allows for more direct visualization of wall temperature and heat flux results, as well as flexible blanking options that I'll demonstrate during the demo portion of the webinar in a few minutes. Secondly, text-based data for thermal wall BCs has been moved to a new dedicated output file called thermalwalls.log. This file contains information about the total heat transfer from all thermal walls, as well as average surface temperature and heat transfer information for each thermal wall BC. Baffles have also been updated in version 25.1. A new feature that's been added to allow for user-specified filtering of particles by size is pretty interesting. When a particle is flowing toward a baffle, the specified pass-through probability will determine the likelihood of that particle passing through the baffle. This is controlled through the use of a pass-through probability file. It's similar to a PSD file in that particle size is present and there is no time dependence. Each particle size is specified along with positive and negative pass-through probability values. There's no limit to the number of rows that can be used, and there's the option to interpolate between rows in cases where you want to do that. To illustrate how this new size-based filtering capability can be used, we've simulated a field-scale downhole sand control screen model. The model geometry is based on the work of Wong 2016, and we've applied flow BC and pressure BC definitions to illustrate the filtering of particles. This simulation models the complex geometry of a sand control tool, which includes a base pipe, a shroud, and the inner metal mesh layers. A baffle is implemented in the model to efficiently represent the complex geometry of the perforated shroud and the inner mesh layers. By using the new size filtering feature, we can accurately filter sand particles based on their specific size, just as the real-world equipment would do. The top image and animation illustrate the full tool geometry, which includes a base pipe and shroud, and there's also a cross-sectional view of the domain in the top right. Below this, an animation shows two separate cross-section views taken from the same simulation but using different blanking constraints. The middle animation shows large sand particles, which are above 50 microns, being filtered by the baffle. Since they're not allowed to pass through the baffle, they build up and flow to the bottom of the outer pipe. The bottom animation shows the distribution of finer sand. These particles are small enough to pass through the filter, demonstrating the model's size-selective filtering capability. This is a powerful approach for simulating, analyzing, and optimizing the performance of critical downhole sand control equipment. Another enhancement to baffles in this release is faster processing speed. Simulations with large numbers of baffles or with very high aspect ratio baffles will see the most benefit. Results will depend on your specific geometry, but in our testing we saw some cases that were able to process baffles up to 10 times faster with the new method. If you're using baffles as heat transfer surfaces, be aware that we've moved the text-based data to a new dedicated thermal baffles.log file. This file has the same structure as thermal walls.log and should allow users to find all the heat transfer information more conveniently in a single location. Switching gears a little bit, we've added a new option to rotate output data in simulations that are using rotating gravity. This option is on by default for new projects and enables much more convenient post-processing for rotating simulations. Visualization data in TechPlot is rotated based on the user's specified axis of rotation and rotation velocity, and animations can be directly exported without having to use a script. Text-based output data, such as raw data, is also rotated in order to make data analysis more convenient. The animation on this slide shows a Barracuda simulation of an auger using the new rotate output data feature. We'll take a closer look at this example in the demo portion of the webinar as well. In this release, we've also made a new default option change. We've enabled the nonlinear temperature solver option for any new projects that are created in this release. This feature was actually added in 25, but it was defaulted off. But we found that it has positive effects for all cases that we've tested. It allows for higher accuracy of material property calculations, and in many cases also results in faster simulation speeds. We've also added some extra information into flux planes with raw particle data. So if you have a flux plane that's either internal or at a boundary condition, raw particle data will now include the position of particles as they pass through the flux plane. You can see here in this screenshot, columns 3, 4, and 5 are XYZ position of the particles. And this will allow you to perform detailed analysis based on particle position, which can often be important. Finally, we do have an important system requirement change that we want to make sure everyone is aware of. Starting with this release, Red Hat Enterprise Linux 7 and CentOS 7 are no longer supported, and Barracuda will not run on these systems. So if you are currently running Linux with either Red Hat or CentOS 7, we recommend that you upgrade. And this table shows a number of options that you could potentially choose from that have end-of-life support dates out several years. So we definitely recommend that you update your operating system to one of the options shown here. Okay, now I think we will switch gears to the live demo portion. So here I'll show a Linux system where we have a few of these cases set up. The first thing that we'll show is the ability to specify heat transfer rate and heat transfer flux. This is our familiar gasifier training problem, and as many of you are probably familiar with, it has a series of heating coils within the fluidized bed. And so we'll show how we set this up in order to specify a heat flux instead of a surface temperature. And then we'll come back here and we'll look at the results a little bit more. So here we're in the Thermal Wall BCs section of the GUI. And if we edit one of these, we can go to the Thermal Wall tab. In this case, we are using a transient file. In general, we recommend using transient files because you can always interact with the solver and change your specification as the solver is running. But what we're seeing here is this specification has been set to a heat transfer flux of 9,000 joules per meter squared per second. And one thing you'll notice is if you use either heat transfer flux or heat transfer flow rate, the GUI will require you to specify a minimum temperature and a maximum temperature. And these are used to make sure that, that the wall temperature always stays within a physically reasonable upper and lower bound. So based on your knowledge of your system, specify a minimum and maximum temperature, and then the solver will target the heat flux or heat flow rate that you've specified. One thing to note is that this column is similar to a few other columns that people might be familiar with in SFF files in that you can change the basis of this. And in order to change it, you double click on the column header, and then it allows you to say, okay, I want this column based on temperature, or I want this column based on heat transfer rate. And so this is how you change the basis of what is being used in the SFF file. If you use temperature, you'll see that the minimum and maximum temperature columns are grayed out, so they're not used, and the values there are not read by the solver. So I think the GUI will automatically default some values for you if you have temperature. And then you can switch to heat transfer rate or flux by double clicking there. The other thing you'll notice is that you can also do this for specify values if you desire. You can use temperature as you always have, or you can choose heat transfer rate or heat transfer flux. And again, minimum and maximum temperatures would be required in those cases. So I'll go ahead and cancel out here, and let's go back to TechPlot. One of the things I mentioned during the presentation was that by virtue of putting some of this information on walls zones in TechPlot, it allows us to do some nice things with post-processing. So one of those things is, like you're seeing here, we can visualize the geometry of the system, and we can make it like a transparent gray to show what's happening with the internal geometry, and then we can separately show data on the heat transfer surfaces. And so that's what we've done here, so that we can really highlight what's happening with these heating coils. The other thing that we've done here is we've used blanking. And so here I'm going to click on this frame, and let's go to the blanking definition. Plot, blanking, value blanking. And what we'll see here is we have blanked all the surfaces where the wall heat flux is less than 100. So essentially what we were going for was was blanking all of the adiabatic walls where the heat flux is 0. And so if I disable this blanking criteria, we'll see that all of these outer walls, they have a temperature value because they are near cells, or they are at cells where the temperature is varying. But they obscure our view of the heat transfer coils that we're really interested in. So by using this sort of blanking criteria, we can hide all of the walls that are not doing anything and get a nice view of just the heat transfer surfaces of interest. The other thing that we're showing here are a couple of XY plots, and these plots are pulling data from the new thermal walls.log file. And if I double click on one of these data sets, it should bring up the mapping style dialog. And I realize some of these are kind of a faint gray, but this is the set of information for this simulation that is available in the thermal walls.log file. So it's pretty easy to show things like the average surface temperature of each of the thermal walls, or the heat transfer rate from each of the thermal walls. Those things are pretty easy to find and plot. As you may be familiar with, in previous releases of Barracuda, this information went to trans.dat files, and it was kind of mixed in with data point information, and so this should make it easier by virtue of having a dedicated file. Okay, let's go to our next example. This is the sand screen example that we discussed a little bit earlier, and I wanted to show how this case was set up using a baffle. And so we can see here there's kind of this brown line, and what we're viewing here, like this simulation is 3-dimensional, but we've put on some blanking constraints to get kind of a 2-dimensional view that makes it easier to understand what the baffle's doing. So we have a baffle that is not allowing particles greater than 50 microns to pass through. So in this view, we see that all of the large particles, as they're flowing in, they tend to go down and around to the bottom of the system and collect there, whereas small particles are allowed to flow wherever they want, and if their flow path happens to be toward this baffle and through the baffle, they're allowed to pass through. And so let's take a look in the Barracuda GUI at how that is defined. Okay, so this is within the setup grid section of the GUI, and we've placed a baffle in this geometry, and where this is controlled is under the properties button. So if we click edit under properties, we'll see that we have directional particle filtering enabled, and we have a pass-through probability file that's being used. So if we edit this file, we'll see in this case these two rows both have 100% or a factor of 1 pass-through probability, so 100% probability for both the positive and negative directions. So any particle that's between 1 e to the minus 5 and 50 microns in diameter can freely pass through this baffle. Any particle that's 50.01 to 300 has no possibility of passing through the baffle. And so this is kind of a simple illustration that it's either completely able to pass through or completely unable to pass through. You can also put values that are between 0 and 1 to do fractional probabilities. So you don't have to have a really sharp cutoff, but in this case, that's the definition that we used for showing off the feature. Okay, let's move on to our last demo example here. So this is the example that was the auger that we showed in a video. So in this case, we are using this feature to rotate about a major axis. And this feature has been available for a few versions now. I don't remember the exact year we released it, but it's been a year or two. So for rotating systems, especially things like rotating drums or other kind of slow rotation systems, you can rotate the gravity vector around an axis of your specification, and you can specify the rotation velocity. And if you use this rotate about major axis feature, by default in this release, you'll see that the rotate output data option is checked. And really, this does make life a lot easier if you are running this type of system and you want to make animations. So here I'm going to back this one up to time 0. And just before I do, what we're showing is just particles by residence time to make it easier to see. Like the blue particles just got into the system. The red particles have been in the system for up to 30 seconds at this point. So I'll go back to time 0. And if we press play, we'll see that the auger starts rotating. And this auger is modeled as a baffle structure. In this particular case, that's why it happens to be that kind of orange-brown color. And the nice thing about this, compared to previous releases, is that you do not have to use any sort of like PyTechplot script to manually rotate the view to make it look like a rotating system. And so here we can see I put an orientation axis here. The z-axis of the orientation axis is always pointing up. And really we can think of this as like the z-axis is always pointing relative to our gravitational vector, and that vector is rotating around. But instead of this whole axis rotating, we're rotating the geometry so that it appears natural as a rotating system. And so this can be pretty nice. So for users who are using that rotating gravity feature, hopefully this will be useful to you and make your life a little bit easier as you're making animations and images to convey your results. Okay, I'll go ahead and stop this, and we can hand it back over to Rosemary, and we can go back to presentation mode.
All right, well, thanks, Sam, for that demo of Barracuda version 25.1. We're now going to transition over to our Q&A session, and I encourage everyone to submit your questions now via the question panel. We'll start answering them in just a few minutes, so don't miss this opportunity to get your answers directly. And while you finalize those questions, let's briefly explore the various ways you can start leveraging the power of CPFD. So software licensing is the direct approach where your team takes the lead using Barracuda in-house for setting up, running, and post-processing your simulations. Whether you prefer running on your own hardware or utilizing the cloud, our global enterprise options make it easy for teams worldwide to collaborate. We offer a variety of licensing models, and our sales team is ready to discuss the specific solution that fits your needs best. If you're an existing Barracuda user, you might be ready to scale up. Whether you want to add license tokens to run more concurrent simulations or upgrade from single GPU to the impressive speed of multi-GPU processing, please reach out to our sales teams. We can flexibly add solver, chemistry, and/or GPU tokens whenever you need to meet evolving project demands. We also offer engineering services for customers seeking the engineering benefits of modeling their systems with Virtual Reactor, but who might not have the capacity or in-house staff available to do so on their own. So contact us if you want to learn more about this option. And if you're eager to get started using Barracuda hands-on, attending one of our web-based engineer-led training classes is a great option. Our next class is coming up in December, and we'll have more information about that in a couple slides. And training can be combined with project work and licensing through our Quick Start program, which gets you up and running as quickly as possible. CPFD sets up and runs the first model for you, and then we hand it over to you, train you on the software, and then provide the software licensing. This allows you to build out your own in-house capabilities with a model that's already up and running. Finally, we work with people in a variety of custom ways through R&D partnerships, and this can be direct with us or collaborative with our other strategic partners. So contact us if you're interested in becoming a partner. And now we have some upcoming events that we'd like to highlight. So ERTC is coming up next week, and CPFD's Vice President of Engineering, Dr. Peter Loizos, will be speaking on optimizing environmental and economic considerations with virtual reactor simulation. In addition to the presentation, CPFD software will be exhibiting at ERTC. Visit our booth to discover how Barracuda Virtual Reactor is empowering refiners and innovators to improve efficiency, accelerate development, and meet decarbonization goals with confidence. Additionally, CPFD software is proud to announce that together with partners EvoPhase and the University of Birmingham, our joint project, Autonomous Design of reactors using AI has been selected as a finalist in the 2025 iChemie Global Awards under the Oil, Gas, and Energy Transition category. Winners of the awards will be announced on November 20th. Another event we'd like to point out is that CPFD regularly schedules web-based training classes for people interested in learning about Barracuda. Please contact us if you'd like to join our last class of 2025, which will be held December 8th through 12th. And finally, CPFD is excited to announce that we'll be hosting our next webinar for the Barracuda Application Model Series on December 10th. The topic of the webinar will be proppant flow, so keep an eye out for email announcements and be sure to join us. And now we're ready for questions. So be sure to add your questions if you haven't done that already, and then we'll get started. Okay, so we'll start with this. I'm going to ask the questions and then Sam will answer them. Can heat flux at thermal walls be used to model cooling?
Yes, it can. So the example that we showed for the gasifier had heating coils. So those were, by our sign convention, we put a positive value for the heat flux. If instead you wanted to model cooling coils, you could use a negative sign in front of that value, and then heat would be pulled out of the system by those thermal walls.
Okay, yeah. Great. Good to know. All right, and our next question is, can baffles with particle filtering be used to model filters that have a large pressure drop?
Yeah, this is definitely possible. So as I showed in the edit dialog, and here we can jump back into that portion here. So I'll show this Linux machine again. This is the wrong baffle. My apologies. Another baffle case. So here for this sand screen, you can definitely also specify K-factor values if you have a baffle that's also filtering particles by size. This baffle can also act as a thermal baffle to act as a heat transfer surface. So any of these physical behaviors of the baffle can be used simultaneously.
Okay, great. That's good to know. All right, here is another question. Is there a way to move baffles during runtime of the simulation?
So currently this is not possible to do. It's something we can certainly put in as a feature request for the development team to consider. But as of today, when you define a baffle in Barracuda, you define its position, and that position does not change over time. Maybe the closest thing that we really have to moving structures like this is really like this auger example, and we've worked with a few different companies who were processing different types of particles through auger-driven reactors, and so this is like our closest capability to what's being asked there. Yeah.
Okay. All right. Okay, I think we have another question here. Okay, can you model mechanical blending with rotating agitator but stationary wall?
Oh, okay. Yeah, so this is kind of a common question that people do want to do this with Barracuda. So we do have some limited support for doing this, and it's in what we call the beta mode of the software. So this is like features that are in development but are not fully released. I see who has asked this question, and we will reach out to you and contact you and show you what the options are that are available in beta mode. I would say there are kind of some caveats about what types of systems it's appropriate for, but yeah, we have had some people use that with success as well.
Okay, we have another question. Okay, is there a way to track bubbles in liquid media?
Okay, yeah. So this is I think this was a question that someone sent in before the webinar, yes. which is great. That's always awesome if people have questions to ask. One thing we didn't really touch on in any of these examples was the idea of a liquid domain in Barracuda. But you can definitely do this, right? So Barracuda can be used to model things like ebulated beds or liquid settling vessels where particles are settling in a vessel full of liquid. And we do have the capability of tracking discrete bubbles that are composed of gas species. And so we use some of those the same calculation methods that we use to track particles can also be used to track bubbles. And so, yeah, that is possible to do. I would recommend that you go to our website and search for the term ebulated bed, and you'll find that we do have a support site post about it, like a supplemental training example, and we have some videos that show that capability in detail.
All right, great. Thanks.
Let's see, we have a few more questions coming in. I'm trying to make this window bigger.
Okay.
There we go. Okay, yeah, let's take a look at this question.
Okay, can you model the attrition of particles inside a high temperature horizontal pyrolysis reactor as volatile components? As the volatile components are driven off through wall heating.
Okay, yeah, so a couple of different aspects to this question. So one, the volatile components aspect, yes, that's definitely possible to do with Barracuda. And so, like one of these examples, this gasifier example, it has volatiles defined. And so this kind of illustrates like, okay, I have some volatiles that are trapped inside my particles, and I can specify what is the composition of gas species that are evolved as the particle heats up. And you can specify something that kind of looks like a reaction rate, sort of Arrhenius equation, to describe that rate of release. So that capability is definitely there. When this happens, the assumption that the solver makes is that the particles maintain their current size, but their mass goes down, so their density goes down. One thing that we are not currently able to do is the attrition of particles. And so like a given particle cannot break by virtue of a physical force in the solver. So be aware that that aspect of it is not currently supported. But the other aspect of evolving things or of releasing volatiles from the particles can be done.
Okay, great. All right, I think that we're done with questions at this time, and so we're going to end the webinar now. Thanks for joining our webinar today.
Yeah, thanks, everyone.